Good morning, dear students. I am Dr. Srinivas Bathini, Professor of Chemistry. So in the last video, we have seen the displacement of electrons, that is belonging to fundamental concept 2. That is inductive effect, we studied already. That is the first one. And the second displacement of electron is resonance effect or mesomerism. The topic is what? A resonance effect. Resonance effect, or we can say mesomerism. Mesomerism. So mesomerism or resonance effect. What is meant by resonance effect? The phenomena of existence of two or more canonical structures differing only electron distribution, but not in the relative position of atoms, is known as resonance. It means sometimes it's not possible to represent the molecule with only one structure. More than one structure has to be proposed, but all the structures not explain the observed properties of the molecule. So we have taken an average of all the structures, which is explain all the properties. That is called hybrid. What hybrid? Resonance hybrid. This is referred to as the resonance or mesomerism. All these resonance mean the hybrid resonance structures are hypothetical and an imaginary structures. Hypothetical or an imaginary structure. The energy of the resonance hybrid is always less than the imaginary structure or canonical resonance structures. For example, we have to see in the benzene structure. We know the benzene structure that is proposed by the Kekule and Devor. We know that Kekule, two structures of Kekule benzene. The two structures proposed by the Kekule and three structures proposed by the Devor. We can mean two Kekule structures, three Devor structures. Total 5 canonical structures of benzene. Benzene is having how many canonical structures? This is the hybrid, resonance hybrid. So benzene total 5 canonical structures. Total 5 canonical structures. And one resonance hybrid. This is called the resonance hybrid. Resonance hybrid. Resonance hybrid. So what are the 5 canonical structures? We will draw it. Before going to draw, we have to know the bond order of benzene. That is the bond order. Carbon in benzene. There is a carbon. The bond order is 1.5. 1.5 bond order. And bond length, the bond length is 1.39 angstroms. Bond order is 1.5 and bond length is 1.39 angstroms in benzene. If we can take the C double bond C bond length is 1.20 angstrom. This is the bond length between the bond length between the carbon, single bond carbon is 1.39 angstroms and bond length between the two carbon double bond C is the 1.2 angstroms. Mean that is between the 1.3 angstrom between the 1.2 angstroms and 1.39 angstroms. And one question why benzene has extra stability and it does not undergo electrophilic addition reactions. It has extra stability and it does not go under electrophilic addition reaction. What is the reason? This type of questions will ask. So due to the what? Resonance. But it shows electrophilic substitution reactions. Only electrophilic substitution reactions. electrophilic substitution reaction. Electrophilic substitution reactions. Okay, so now we have to see so what are the 5 canonical structures? Everybody knows, just I will draw it. So what are the 5 canonical structures of benzene? The Kekule proposed the 2 canonical structures. The Kekule proposed 2 canonical structures. So what are that? We know already, everybody knows, these 2 are the canonical structures of the benzene proposed by the Kekule. So these 2 are first and second 2 canonical structures proposed by the Kekule scientist. And Dewar structures. Dewar proposed 3 structures. What are that? This is the benzene. This is the one structure. This is the one structure. And this is the second structure. And this is the third structure. So first, second and third. So 2 structures are proposed by the Kekule and 3 structures proposed by the Dewar. So total 5 canonical structures. 5 canonical structures. 5 canonical structures. And only, so these are all imaginary. Only this is the resonance hybrid. So resonance hybrid can write like this. This is the resonance hybrid structures. So this is the one example. The benzene canonical structures are resonance structures. We can say resonance structures. So we have to write the resonance structures of 2 Kekule and 2 Dewar. If you take another example, especially in the exams, they will give you. So can you write the? Can you able to write the phenol canonical structures? Phenol, that is important. Phenol. So phenol mean, we know that phenol structures. So this is the electron displacement. Remind everything the displacement of electrons. So this is the phenol. We know that phenol OH. So oxygen having the electrons, 2 lone pair of electrons. You know the 2 lone pair of electrons. So and benzene. This is the this we can say phenol. So this is the first structure. So we can write like this. And if the electrons, the 5 electrons are displaced from here, and this lone pair of electrons come to this side. So what happened? So that oxygen gets the positive charge and this carbon gets the negative charge. So we can write like this now. So and this structure we can write like this. And if you can write now, we can write like this. So here this the pi bond, this pi bond. So if the pi bond comes to this side, what happened? And the electrons are displaced to here, from here to here. So this is the second structure, and third canonical structure formation takes place. Third canonical structure formation takes place. This is double bond. This is the third structure. And similarly, this pi bond come to this carbon atom, and this one come to this side. So what happened? And this structure will come. Okay, this is the fourth structures. So how many total 4 canonical structures are possible in phenol? Total 4 canonical structures. Okay, just one example of benzene, another example of phenol. So you have to write all these are possible in resonance effects. So how many types of resonance effects are there? There are the 2 types of resonance effects: electron withdrawing resonance effect and electron releasing resonance effects. So there are 2 types of possibles. So that depend upon the displacement of electrons. minus resonance effect and plus resonance, because that is dependent upon the completely displacement of electrons. So we have to see the electron withdrawing resonance, mean EW. So there are two types of electron withdrawing resonance effect. We can say resonance effect. So electron withdrawing resonance effect, or minus R or minus M effect. So here the group or substituent that withdraw electrons by delocalization mechanism from the rest of the molecule. Due to this effect, electron density on rest of the molecule decreases. Once again, please read the group. So whatever the group, nitrogen dioxide or sulfur dioxide, nitrile group, whatever the group present on that benzene ring or substituent to aldehyde groups or carbon monoxide and keto group, sulfonic acid group, whatever that groups are, these are all are the electron releasing groups. So what are the electron releasing groups? That groups withdraw electron density, withdraw electrons by delocalization mechanism from rest of the molecule. So due to this effect, electron density on the rest of the molecule decreases. Example, that what are that groups? For example, NO2 group, nitrogen dioxide is present. So this is highly electron releasing groups. We can say sulfur dioxide, it is also can release the electrons. Nitriles, aldehydes, ketones, these are acids, all groups, acid groups. And COX, acid chloride, and acid amide, CONH2. So if all these are present in that group, so what happened? These are the electron rich. So electron withdrawing nature groups are present on that that's molecule. So what happened? So they are withdraw electrons by only delocalization mechanism. Mean the electron density on rest of the molecules. Okay. For example, if you can see the example, we can understand. For example, nitrogen cyanide group is there. For example, CN substituent and present if propyl. For example, we have to see the CH2 double bond CHCN. For example, this compound. This compound is there. For example, this one. So here what happened? The carbon triple bond nitrogen. This is cyanide groups. So here what happened? The pi electron displaced towards nitrogen. So nitrogen gets the negative charge electron rich group. And what happened? These pi electrons come to this side. So what happened? This carbon gets the positive. So now CH2 plus CH double bond C double bond N. So this one happened. Mean CN substituted in, this is called the acrylonitrile. The CN substitute in acrylonitrile due to delocalization of molecule, delocalization of electron. Which electrons? Pi electron. These are the pi electron. Delocalization of pi electron decreases the electron density of third carbon atom, that is the CH2 plus 1, 2, 3. So delocalization takes place. So this happened due to the resonance effect. So this happened because this is the electron withdrawing groups. And second one is the electron releasing groups. That is the plus R effect or plus M effect. So electron releasing group means the group or substituent that release electrons, not withdrawing electron, release the electrons, the rest of the molecule by delocalization of pi electrons. Due to this reason, the electron density increases on the rest of the molecule. Here the density is increases, whereas in the electron decrease in the rest of the molecule. So see that what are the groups are present. So this is electron releasing groups, that is ER, electron releasing R plus R effect, R plus M effect. Okay, so what are the groups are there? For example, O minus, electron rich group, NH2 electron releasing group, NH2 minus, NH2 minus, or NHR, we can say NHR, NR2, or OH, or OR, SH, or SR, NHCOR, so all these things are finally alkyl halides are there. Halides, chlorine, bromine, iodine, these are halides. So these are all our electron releasing substituent groups. If this group is present on that compound, so what happened? That the density is increasing. The density, electron density is increasing. For example, just before we have seen the phenol group. The phenol, OH group is present on the benzene. OH group is present. What happened? The electron density increases on benzene ring due to plus R effect of OH group. Once again we have to see that. So for example, this is the phenol. So here what happened? So this lone pair of electron come to this side. This one is come to this side. Then here this one come to this side, and this one come to this side, and this one come to this side. So like this. Just before we have seen that is the phenol. So the OH group on benzene, what happened? The electron density increases on benzene ring. Electron density is increases over the benzene ring. Complete rest of the molecules. So due to what? Plus R effect of OH group. Plus R effect of OH group. This is the OH group. Or if OR is also present like the same thing, NH is aniline. We can say aniline. If you take the aniline, another example. This is the another example. Aniline also same case. If ethers are present, same case like this. Or SH or NHCOR are same. All electron substitute and electron releasing groups are same thing. So these are the some displacement of electrons, that is the electron resonance effect or Mesomerism effect. And what are the rules are present? The rules are important. So what are the rules to give the resonance effect? So that they must be valid Lewis structures obeying the octet rule. They must obey the octet rule. So every resonance compound obey the octet rule. The 8 octet state must be there in every atom. So without that is not possible. I will tell you the examples. They should possess same number of electrons. Same number of electrons must be there. Or equal net charges. Either left side or right side, that is the equal net charges should be there. The Lewis structure and obey the octet rule and possess the same number of electrons and equal net charges. The number of unpaired electrons in the same must be same. Unpaired electrons must be. The position of atoms should be same in all the resonance structures. The position of atoms. The position of atoms, all the resonance structure must be same. So for example, OH, this is the same. The position of the OH group is same. So see that is very important in this one. The atoms that are part of the delocalized system must be changed in one plane or nearly the same region. Get the maximum overlap between the two orbitals. Maximum overlap. Because all our pi electrons are there. So the overlap takes place between the two atoms. The resonance structure may or may not be equivalent. The resonance structures. The bond order to connecting the atoms may vary between the two different structures. different structure. In this, in phenol, 5 canonical structures are there. So the 5 canonical bond order is very different. So higher 1 or 2 cases. So for example, we have to see that canonical structures, some compounds. This is very important for IIT students especially. So what are the compounds not obey that resonance structures? I will write the one example. So for example, CH3N. So this compound we have to take. So this compound here plus and here minus, plus and minus. And resonance structure is CH3 and N, CH3 N. So both the double bond. So in this, is it a correct structure or not according to resonance structure? So what is the defect in this? What is the defect? Is it resonance structure? No, it is not correct. Because the valence of nitrogen, see the valence of nitrogen in both the structure exceed the 5. It's not valid. It's not valid. So this is important. So the resonance structure is there, but the excess, the obey the octet rule, that is the excess, the exceed 5 electrons. Exceed 5 electrons. Okay, this is important. If we take one more example, butadiene, in the case of butadiene, CH3, CH double bond, CH2. So this is the butadiene, we can say butadiene. It is also not valid. So these are the very important for the competitive exams. So one more example, we can take the keto and enol structure. For example, acetone, we have to take the acetone CH3, CO, CH3. And this is the keto form, you can take the enol form. This is the enol form. Keto, enol. Keto and enol are not resonance structures. These are not resonance structures. The position of hydrogen atoms not same. Here the position of, there is no hydrogen atom here. The position is changed. The position of hydrogen is changed. So here hydrogen is there. There is no hydrogens. The position of hydrogen atom not same. Hence it is not valid. It's not valid. Okay. So these are the sum. If in the case of stability of resonance structures, what is the stability? How can you determine which structure is having the more stability? For example, you have to take that is most important in the stability. So these are the important for the competitive exams. Especially we can take the this structure oxygen. We have to take the oxygen having the 2 lone pair of electrons, and CH2 group is there. That is the carbon plus. In this case, so this is the first structure. If the electrons are displaced from here to here, so how can you do this one? So if this one, this structure, okay. So this is the structure. So the plus, here the plus is there, the carbonizing, here the plus is there. This is the first one and the second one. According to stability, which one is the more? According to resonance, the stability of the structure, which one is having the more structures? These 2 compounds. So which one, the first or second? In this, the second is more stable due to the what? Due to the all the atoms have octet rule. All the atoms have octet and more covalent bond than the first. More covalent. Here all are octet and more covalent. So that is because this is the more stable one. More stable structure due to the resonance. Because the octet, this obey the octet rule and having the more covalent structure. In the case of we have to take acetic acid. One example I will tell you. So please tell me that one. So CH3 COOH CH3COOH. Here the lone pair of electrons are there, 2 lone pair of electrons. Here also 2 lone pair of electrons are there, 2 lone pair of electrons are there. And if remove the hydrogen atom, and 1 negative, so 2 1. Okay, 2 electrons are present. So this is the one structure. And if you remove this one also, the double bond, so put so otherwise simple minus, and this become plus because this is the plus. So these two compounds, the first and second, which is having the more stable, and why these two compounds. So the resonance structure of second, this one, is invalid and less stable due to more charged. Mean the charges are more. Here 2 negative charges, 1 positive, 3 charges are compared to the first structure. Here only 1 negative charge is there. The first one is valid and more stable due to less charges. Only 1 charge is there. So this is about the displacement of electron. And we know that the displacement of phenol. So among the phenol, we know already the first structure is the most stable since it has no charges, whereas second and fourth have less stable and more stable than the third. So mean in phenol, already I told you 5 canonical structures. Among the 5, the first one is the more stable. Okay, one last example. The last one is we know that for example, acetone is there. Acetone structure, CH3CO structure, we can write. That is the last example. I will tell you that the displacement of electron, it's very important for IIT students. This is the acetone. How can you write that? This is the acetone. So we can write in two types of resonance structure. We can write this molecule. We can write this one double bond CO. We can write CO. So here the lone pair of electrons, 2 lone pair of electrons. If you get the negative charge and 2 lone other electrons will come here. Okay, and CH3 is the same. So this is the one structure, and one more structure we can write so there is no extra electrons. How can you write the CH? This is the C double bond CH3. Here the 2 lone pair of electrons are there. So here remove 1 hydrogen, we can write the positive charges. So in these 2 cases, so which one is the most stable and which one is the less stable? So definitely everybody knows the first one is the more stable than the second one, because the acetone, there is the positive and negative is there only because the 1 charge is there here. Here 2 charges are there. So here because the positive charge and this is the negative charge. This is the negative charge. Here the negative charge. We can write the negative charge. And here the more electrons are there. Here the less electrons are there. Mean the first one is the more stable form due to the conventional charges are more stable. Conventional structure are more stable. It means generally oxygen is a negative atom and carbon is a positive conventionally. So always say the CH3 plus carbonium ion. So oxygen always name. These are the conventionals. If this is the positive, this is the negative, this is the opposite one. So mean this is irreversible. So always the conventional charges are more stable than the unconventional charges. Okay, so thank you very much. So next video we will discuss the electromerific effect. And thank you very much. Thank you.